Please give
Yeah,
me a
sure.
thumbs up,
Yeah.
everyone. Give me a thumbs up, everyone. Perfect. 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 Thank you. Thank you so much. Vipul, I think we can begin the session. I'm muting everybody's mic for the time being. I think Vipul, we can start the session.
Yeah, sure. Thank you, Krasna. So good evening, everyone, and welcome to today's session. So I hope my slides are visible, and please tell if they get freeze in between or some issue comes up. So as you know, I think we all belong to semiconductor industries, and semiconductors are inherent part of our day-to-day life. We cannot imagine our lives without semiconductor. But I think most of the us know that semiconductors are part of our life, but we do not directly correlate with them because ultimately we are not using them directly as the end product. What we are using are like devices, laptops, smartphone, etc. So the idea behind this today's webinar, is to maybe give you some background, like how we came to this today's world, like how the semiconductors have progressed over last 70 years since they came into origin. So the idea is to give you a brief history and also to give you some context about semiconductors, like because there are different technologies around us. We are surrounded by different technology, automobiles, space, medical, everything. So semiconductor is one of those, but the kind of impact which they have put on our lives in at least specifically in last 20, 30 years is mind-boggling. So that's a little effort from my side to give you some brief overview for history. So let us start. So before understanding what exactly a semiconductor, we need to understand what basically is technology, because we use this term a lot. We talk about like these different kind of technologies. There is a medical, like there is automobile, aerospace, different kind of tech. But what exactly is technology? So there are different kind of inventions which keep on happening. We all know about Einstein or Newton. So they were great scientists. So they invented something. But do we remember or do we compare them with Steve Jobs or let us say Sundar Pichai or Satya Nadella? No, because those people, they were real scientists and they invented something. But then ultimately to convert that invention or scientific discovery into a product, that is the role of technology. So basically, applying the systemic application of whatever scientific knowledge which has been basically developed or invented for making a practical use in day-to-day life or for the betterment of a humanity. That is what technology is. So scientific invention is of no use to general humanity until or unless some kind of a real product comes out of it. So that is what technology refers to. And in our case, specifically, since we belong to semiconductor industry, so we will be looking from today's webinar in semiconductor technology point of view. So just to give you an overview, technology, it might look like it is a new word, but it's not. So there have been several discoveries and several inventions which have happened in past, and they have led to some kind of technologies. Like for the early man, which came, they started using stones and as a tools or the wheel for starting transportation using bullock cart and other means. So that was a kind of a, like you can say, state of the art technology at that time. Then in medieval period, we started using, as a humans, we started using waters and windmills to generate some kind of energy or power, or for grinding grains, etc., all for those purposes. And then compass, when people used to go with their ships for on or their naval vehicles, they needed to know like in which direction they are going. So compass was a big technology for humans of that period. And then came printing press and cannons and firearms. So people who earlier used to fight using swords and other kind of a manual arms, they started using these kind of weapons to fight their wars. So this was again a new technology. And then finally, in industrial revolution in last 200 years, we started using steam engine. So that gave a big boost to transportation, and then telegraphs. So it was a new means of communication to passing the message from one place to another. So these were the state of that art technologies in that period. But now, when we have moved to today's world, so we are using different kind of technologies. So I will refer to them later on. But before that, just to give you a context, I mentioned doing having a scientific discovery is one thing, and converting it into a technology is another thing. So just to give you an examples from the semiconductor point of view, So these are the inventions which have taken place in the world from the semiconductor point of view. Like the transistor was invented in 1947, and then semiconductor heterostructures. This invention was done in 1968. It led to the development of lasers, solar cells, LEDs. Then in 1958, integrated circuit was invented by Jack Kilby. And in 1993, the blue light LEDs, which basically completed the trioka of red, green, and blue LED, because then people were able to develop white LEDs. So that's why it was given the Nobel Prize. And mind you, this prize is not for semiconductor. This prize is for overall category of physics. So these awards for scientific inventions were given for development of physics. But the main takeaway from this slide is you see what is the year of invention and what is the year when they were awarded the Nobel Prize. So it's not like when that new invention was done and in 1 or 2 years time it was awarded, because at that time nobody knew what its significance was, like how it was could be used for the betterment of humanity. It was only like after 9 years, like transistor was given a Nobel Prize. Similarly, for heterostructure, like invention of solar cells, LEDs, almost like after 3 decades, it was recognized to be given as a Nobel Prize, because it was during 2000s or like 2014 when white LED, blue LED was given the Nobel Prize. So it was only after 30 or 40 years, or maybe sometimes 3 to 5 decades later, like that significance of that invention was taken note of by the Nobel award giving agency. So the main takeaway from here is like scientific inventions, although they are important, but they are not of use, and they are not for the well-being of us, humanity, until or unless some technology comes out of that. So these are four fundamental inventions which ultimately led to the growth of semiconductor industry. Okay, so this gradation of different technologies which were most influential in last century, that is in 1900s, in last 20th century, it was done by a very like recognized agency in US, National Academy of Engineering. So by their priority, they recognize like these are the technologies which played a major role in development of humanity in last century. So electrification, we all know, if electricity would not have been there, we could not use all the modern gadgets and benefits of it. Then automobiles, they revolutionized the transportation, the way we move from one place to another. So obviously has to be there as one of the influential technologies. Then airplanes. So moving automobiles can only allow you to move from over a short distance, and also that will take a lot of time. But airplane revolutionized the global trade. You can move from one part of the world to another, and also you can trade things. So that was also important. And then fourth one, it is very unique, or you might seem like why it has taken place here. So water supply and distribution. Obviously, what happened like before people could make the arrangement of distributing water from water source to their homes or the place where they are living. The most of the civilization used to dwell around the water bodies or along the rivers. So having the mechanism of distributing water from a water body to a place where people can live, it helped. Basically, it improved the public health, because then you can control the flow of water, and also you can do different steps to purify it. And also, it led to the urban growth, because then people need not settle down near only rivers. Because earlier, if you might have read in your history classes, most of the civilization like Indus Valley and Gangetic Plains, all the civilization used to dwell around the rivers only. But because of this, people could move to some other urban places and then they can dwell over there. And obviously, fifth, electronics, because it laid the foundation for all the computing and all the communication benefits which we are seeing now. So, but these are the inventions which were important or which played major role in last century. But now, in today's world, so these some of the inventions in last 25 years. So these refer to the current century. So I think most of you agree, without internet and Wi-Fi, we could not imagine the world today, the way we are connected together, and also the way it has affected several other domains. So obviously it has to come there. Then smartphones, the real benefit or power of internet has been basically revolutionized by the use of smartphones. Because earlier, even though internet was there, but we were limited to our own places. We could not move from one place to another, having a live Wi-Fi or internet. But with smartphones, we can have that mobility factor with us. So again, that is important. And then social media, because it the way the information can be distributed or can be shared, or the connectivity which can be maintained with people around the world, kind of like whatever physical medium of communication where they all get integrated into a one big social media domain. So again, that was a big revolution. And then genome sequencing. So again, this might look like a little off place here, but now this is also very important because genome sequencing has led to discovery of a lot of new drugs in last 25 years, and they have made a lot of improvement in cancer drugs. Like, so a lot of earlier you might have heard like if somebody has got cancer, there was no scope of them surviving. But nowadays, because there has been so much revolution in cancer drugs, and that has been because of one major factor is genome sequencing, and also in vaccination. So new kind of discoveries which have happened are because of this field of biomedical domain. And then streaming services. Obviously, the way we are consuming content today, or the entertainment, it has already together changed. We are no longer stuck to in front of a TV and have a limited number of channels to view. So, and that also what they are serving us. So now we can have an on-demand view of whatever thing we want to see. Okay, but main again, the takeaway from this slide is all these five fields, and including genome sequencing, they are all dependent on electronics first. And even in electronics, if I try to emphasize, semiconductors play a major role in it. So just to compare, these were the influential fields or technologies of last century, and this is what we have come to. So without semiconductors, you cannot imagine like if all these benefits are taken away from you, can you imagine like how your present world will be? So that's why, again, to emphasize, semiconductor has played a major role in these developments in this current century, and they are going to play a major role in coming rest of the century. Okay, so now let us go a little back, around 100, years back. So let how it started. So we all know semiconductors are important, but in order to compare one technology to another, because generally it becomes a topic of discussion, like which technology or which invention has played a major role in betterment of human society. So I have taken an example of automobile because we know automobiles have also progressed a lot in last 150 years. So let us try to compare like how they have evolved. So on the left side, you can see this was the first automobile which was patented in 1885. So this is like a basic automobile, a kind of a car, or in today's term, we can call it as an auto rickshaw. So this is, we can take it as the origin of automobile industry and how it was beneficial because it again led to the development of transportation and mobility. And obviously, again, it played a major role in developing the global infrastructure, economics, and culture, because these are all the benefits which came later on. But this was the origin of this leap or development for automobile industry. And on the right side, this is a vacuum tube transistor. It looks like an incandescent bulb we used to have in our homes like 20, 30 years back, uh, the yellow color bulb. So this is a vacuum tube, and the role it played at that time was like it can control the flow of current. So that was the purpose for which it was invented. And this was the invention, or we can say this was the origin of electronics industry, and it took place around same time, maybe 19 years later, in 1904. And later on, it paved way for all the modern day developments of radios, computers, and then whatever internet and smartphones which we are seeing today. We can say like this was the origin of all these developments. So this just take a note of this slide. So this was what was around 120 years back. And now let us see how a modern world looks like. So I have taken an example of not a very state-of-the-art car, but a normal car. So this is a Toyota Prius model of 2024, and it has a very decent mileage, kind of a 24 kilometer per liter. So this is a typical modern car which is being used for transportation nowadays. And on the right side are the transistors. So again, these transistors play same role which this vacuum tube used to play 120 years back. That is to control the flow of current. And these are the progresses, and these are kind of, you can say these are the modern latest uh, variation of transistors which are being used to build all the modern ICs or chips. And now you can see like the kind of progress which automobiles have made from this to this, and the kind of progress which transistors have made to from this to this. If okay, this is an hypothetical comparison. If the automobiles would have made the same progress which the transistors have made in last 120 years, so if we take a same measure of improvement or factor of improvement, then ideally the mileage of this car should have been this much. That is 63 lakh kilometer per liter. Can you imagine? So this is the factor of improvement which transistors have made over 120 years. So just to give you an perspective, this is an hypothetical comparison, but just to give you an idea, like this is the amount of improvements which transistors have made in last 120 years. Okay. And then let us see, compare this with some few examples. And we are not going now 100 years back. Let us say we are comparing it like from 40 years back, 4 decades earlier. So this was a computer like in 1982. And this is what our typical laptop looks like in 2024, an Apple iMac. And these are the CPU speeds, the speed at which your processor clocks. So this has increased from 6 megahertz to almost 6 gigahertz. And this is like 1 billion times improvement in the speed. And the memory is like the RAM. It was 256 kilobytes at that time. And now we can get a laptop with 64 GB of RAM memory in it. So it is around 200,000 times improvement. Storage, a typical hard disk at that time was 10 MB, 10 megabytes. And now we can get a laptop with 2 terabytes of hard disk. Again, it is almost 200,000 times. But the interesting thing is just see what is the price. This computer used to cost around $4,000 4 decades back. But this laptop, Apple laptop, costs only $2,000, and this is almost 50% less. And the factor of improvement which you see here, almost like 100,000 or million times improvement in the specifications of that particular computer. And if I again compare it to an automobile, this is a model of Ford Mustang in 1982, and this is what we get now, the latest Ford Mustang. Its mileage has improved from 7.65 to 10, almost 1.4 times improvement. The speed, the like 0 to 60, it clocks in 6.5 seconds. This one does in 2.8 seconds. So it is only 2.3 times improvement. Similarly, the power of its engine from 88 to 480, 5.4 times, and its price has increased 5 times. So just compare these two technologies. So automobile industries, it has made some improvement, but it is very meager if we compare it with compared to what we have seen in electronics. And the price is not decreasing; it is increasing. But just imagine like what all improvement which we have seen in electronics, and all these benefits we are getting at half the price what we used to pay around 4 decades. Okay, so this is the kind of evaluation which we have seen in electronics, and I think not to mention again the major role behind it is played by semiconductors. Okay, so this is a kind of a real life example. A fan at my home got like malfunction, so I was just looking like this is a typical behavior we do nowadays. Like if anything we want to search, we go online and search for a fan. And a typical ceiling fan easily lasts from 10 to 15 years. So I went online and I was looking for a fan, and I was surprised to see like I found this fan online, and these were the features in it. It had a Wi-Fi and Bluetooth connectivity. It can be controlled by my smartphone. It has a voice control. It has a very high efficiency, like it can consume very less power than an older fan. It has a customizable lighting. I can have different kind of colors being represented in it. And then it had obviously had a remote control, and I can also schedule it. Like I can schedule it like it should switch off after such period of time, or it should switch on after this period of. So all these were the features. So this is, I was surprised. Like this is the main function of a ceiling fan is just to give you a cold air, nothing else. But now we see all these features inbuilt in it. Why? Because this is what like people demand, or this is what our technology has enabled it to do. So a simple ceiling fan has basically transformed into altogether like high-tech gadget kind of a stuff. But this is what electronics has done, or this is what semiconductors have enabled. And this is not a thing of this only, this simple fan. I think this phenomena is getting copied to all the equipment which we are using nowadays. Everything is being like it has some piece of semiconductor or some piece of intelligence in it or some kind of a new high-tech feature embedded into it. Okay, so this is just one of those examples. Okay, I think most of us are sports fan and we get stuck to our TVs when we watch cricket. So I don't know like how many can guess what is this on the left side. So this was a very famous dismissal when Sachin Tendulkar was given LBW out when he was trying to duck a short delivery from Glenn McGrath in Australia in 1992, and he was stuck on his helmet. And the umpire was Steve Buckner, and he gave him LBW. Although Sachin was very short in height, but still nobody could believe what was given. Like getting stuck on a helmet and being given LBW. So because at that time you have to believe the word of an umpire. Whatever umpire has given, you have to follow it. If he has given you out, you are out. You have to go out of the ground. But now just imagine nowadays how decision is given in any. This I'm giving an example of a cricket, but it applies to I think almost all the sports. So if an LBW is, if an appeal is made, how an umpire will do? He will track the like where the ball has pitched. He will track the trajectory of the ball, whether it is hitting the stump. If it is hitting the stump, he will calculate that basically the third umpire he has the technology. They will calculate like whether it is missing the stump or not, and then only a final decision will. So just imagine like what all technologies are working behind it, like making a simple decision of LBW. There are first high-speed cameras. They are all around the ground. They are very high frame, high-speed cameras which are capturing all the pictures of ball from all the angles, and then they are feeding it to facing computer or a high-speed or high processing server, which is processing all the information received from different cameras, and it is building a 3D image of that ball, and then predicting the trajectory of that ball, and then it gives all the inputs, all the data about the pitching of the ball, trajectory of the ball, hitting the stump or not. All that information is given to the data in form of the picture, which we see generally on our screens. And then an umpire makes a decision whether the batsman is to be given out. So imagine like how much like succinctly that technology has transformed the game, the game of cricket. And what all are the technologies used behind it? They are high-speed cameras, they are frame grabbers, they are computers which process all the data fed back to them. They are softwares who basically do the calculation and then output the data. And then they are finally display unit, which we also see as the users of a game and on our screens. So these are all the equipments which are used to make a decision whether umpire is LBW out on. So again, not to mention what all comprises of all these equipment are again semiconductor. Without semiconductor, it would not have been possible to do this kind of. And this again, this kind of uh, integration of technology has happened in other games also, like in football. And now to give an offside, there is a technology there. In tennis or in badminton to check whether the ball is hitting outside the line or not. There were again the technology used there. In Formula One, I think technology is being used from last several decades. So just to give you an overview, like as I mentioned about the automobiles or the ceiling fan, again, that sports have also been transformed by electronics or the semiconductors. Okay, so I think we have seen what all transformation semiconductors had done. So now I think everybody wants to understand what basically is semiconductor. So basically, all the materials which are around us, they are basically characterized into two categories. One is conductor, one is insulator. And this characterization is done on the basis of their property, like how well they allow the electricity to pass through them. So we know, like if we touch electric wire to a metal rod or something, our current will pass through it and we will get a shock. But if same with current live wire is attached to a wood thing, you see like no current will pass through and we do not get a shock. Based on the property of a material, whether it allows the current to pass through it, they are classified as conductors or insulators. So the materials like gold, copper, iron, aluminum, they are all conductors. And then these are all the insulator materials. But then there is a certain class of uh, materials in between both of them. So they have a property like the flow of current. So the issue with conductor is like if you allow a current to pass through it. So there is no way to control it. Whatever current is flowing, it will flow through it. You cannot control, like, I want to reduce the amount of that current, or I want to increase the amount of. It's not possible. So, but it is possible with the third class of materials, which are called semiconductors. So the property of semiconductor is like the flow of current, the current passing through them, or the flow of electrons. It can be controlled. You can increase the amount of current flowing through it, or you can decrease the amount of current flowing through it. And how that is done? By basically doping, or by basically putting some impurities or some other element into that semiconductor material. The flow of current can be increased or decreased. So these are the class of materials which are basically used to build all the electronics and the circuits behind it, the ICs or integrated, which we commonly call as chips. So these materials are basically used for that purpose of building semiconductor circuits or ICs. Okay, so I think everybody must have gone through this periodic table sometime in their schools, most probably in your high schools. Uh, so as has been highlighted here, so there are several elements in this periodic table, and I think new elements keep on adding as people discover them. But all these materials which are highlighted in green, they are classified as metals. So they are good conductor of electricity. They can pass the current, and all the materials highlighted in pink, they are insulators, so are also called non-metals. So they cannot pass any current. But there are small group of elements in this periodic table. The technical term for naming them are metals, non-metals, and metalloids. So we commonly call them as conductor, insulator, or semiconductor. So these class of elements which lie in between the on the left side metals and on the right side non-metals are the semiconductor materials. So these are like silicon, germanium, arsenic, antimony, tellurium, and boron. Apart from that, using the combination or building a compound from two individual elements of this periodic table, also some kind of semiconductor material can be created, like gallium arsenide, gallium nitride, or silicon carbide. So they are compound semiconductor. But if I am talking about a single atom or single element semiconductor, so these are the materials which are used to build all the semiconductor chips. Okay, so when we talk about transistors or integrated circuit, I think the story cannot be complete if we talk about something about transistor. So just like when we talk about a car, the first thing we ask is about if you want to evaluate the performance of that car or any automobile. We talk about like how powerful is its engine, how powerful it is, like whether it is how much PHP power it gives. It is 1 liter, 1.2 liter, 2 liter, 5 liter engine. So because all the other things are okay, like you get very good music system, good seats, everything is okay. But ultimately, you do not want a very beautiful car, but with the engine of Maruti 800, let us say. So that's why ultimately the performance of a car is determined by the performance of its engine. Similarly, when we talk about semiconductors, because semiconductor is a class of material, but ultimately they are used to build some kind of circuits are built on those semiconductors. Some kind of electrical or electronic circuits are built, and the performance of those electronic circuits are determined by a device which is called transistor. So ultimately, transistor determines like how good or how powerful or how feature-rich circuits can be implemented on a semiconductor material. So that's why if semiconductor is the whole, like if you talk about a movie, then transistor is the hero of this movie. So we need to know something about it. Okay. So this is how a transistor looks like, and it has three terminals. Although it has four terminals, but majorly these three terminals plays role. So a current passes between two terminals, just like a battery. In battery, we know there is a positive and negative terminal, and current passes through these two terminals. So just imagine it is just like it's not a true representation, but just imagine like it is a battery and a current is passing between these two terminals. But unlike battery in transistor, there is a third terminal, which is called gate. And if we apply a voltage over this third terminal gate, the flow of this current can be controlled. Okay. If high voltage is applied, a current will flow. If a low voltage is applied, current will stop flowing. And this switching property of a transistor is what is used to generate digital data. I think you all must have heard what is digital. So digital data is represented in form of 0 and 1, like high 0, 1, 0, 1. Everything is every data is converted into digital. So this is the property of transistor, which is used to generate those 0, 1, 0, 1 property. And using that transformation of data, lot of circuits can be realized, different kind of circuits can be realized. Whatever features you see actually in your devices, they ultimately, this is what is working behind them. There's a transistor which is implementing some kind of a logic or some kind of electrical property, and that electrical property is finally resulting into whatever feature you are getting from your device. Okay. Okay. Again, to give you an analogy, let us say, for example, there are walls, or let us say there is a tap in your home, and a water is coming to your home from some water body. There might be a lake, let us say there's a Sukna lake or some lake from where water needs to be brought to your home. So can you imagine how it will come? So there will be some pumps or some motors which will take water from that water body, but then that water has to be routed specifically to the tap into your washroom or kitchen, where you want to open that tap and then finally use that. But in between, from that water body to your home, there are several walls in between, and the purpose of those walls is to basically change the direction of flow of current, not current or water. If you open the wall, water will flow in certain pipe in certain direction. If you close it, it will stop, it will move to another direction. And finally, when you open a tap in your home, that's how water comes. So similarly, this is analogy, like you can think of a transistor is kind of a wall or a tap, and using several kind of transistors, and along with transistor there are some other components like resistors, capacitor, inductor. These are all electrical components. Using these transistors, these electrical component, different kind of circuits can be built, and these transistors basically play the role of controlling the flow of current. Like for example, I want to send a signal from this input to this output. So in between there are different transistors arranged in different several kind of combinations of specific architecture, and this is how a signal will get transmitted from one point to another. So that is what role of transistor is. It is similar to what a wall plays when water is trying to be sent from one point to another, from one direction to another. So this is a kind of analogy you think of whenever somebody talks about transistor. Okay, so when I talk about a transistor, I think since we all belong to semiconductor industry, so sometime in your career, you must have heard this term, like what is semiconductor node? We talk about like the SCL has a 180 nanometer node, TSMC has a 2 nanometer node, or some another foundry has this node. So what exactly is that node? So as I mentioned, transistor is a hero of semiconductor industry, and whole semiconductor industry revolves around this transistor. So all the improvements which we have seen are uh, being realized because of the improvements done in this transistor. So this specific parameter of this transistor, the way it is built, it is called gate length. So it is a distance between two terminals on a silicon wafer. So this is a parameter which is called gate length or channel length, which determines the a specific property of a transistor. So this the distance of this parameter or this uh, channel length of a transistor is what's called as a technology node. Because based on how small a transistors can be fabricated, everything revolves around it. Because it is the smallest dimension which is getting imprinted on a silicon wafer in order to build a transistor, and around it revolves all the other technologies which are in that technology or that foundry. So that's why this parameter becomes very important. But this gate length, as a smallest feature size, this representation was valid only up to 22 nanometers. Below 22 nanometer, the kind of nodes which we are hearing now, like 16 nanometer, 10 nanometer, 5 to 1 nanometer, the shape of transistor has changed. So this representation no longer applies. Like the gate length is representing the node of a transistor, but still this is what this basically nomenclature came from. The node of a technology is represented by this dimension of a transistor. Okay. And then loads are also divided into different configurations. So legacy nodes are like the foundries or technologies which are still using transistors with 90 nanometer channel length and above. Then mature nodes are these, and then advanced nodes or leading edge nodes are what we are hearing nowadays, like whatever Intel or TSMC they are fabricating. They are fabricating transistors which are less than 10 nanometer channel length. And they are all used for fabricating or developing all the high-end electronics chips for CPUs, GPUs, and SoCs. Okay. So this is what a node represents. So whenever we talk about like this foundry, this nanometer node, so this it means like the smallest transistor which they can fabricate will come to that number, like 180 or 90 nanometer or 65. Okay, so as I mentioned, the big development in semiconductor industry, a big hand behind that is of transistor also. So this is a comparison of how a transistor has evolved. So when I talk about like this is 10 micrometer channel length transistor in 1971. So that was the state of the art transistor that could have been fabricated at that time, 50 years back. And today it is 2 nanometer. So if I go back again, so if I'm in 10 micrometers, so this distance was 10 micrometer for this transistor. This is what could have been fabricated in 1971. And nowadays it is 2 nanometer. So just imagine how much improvement has been made. 5,000 times smaller transistors can be fabricated now. Okay, and then up the maximum number of transistors which can be fabricated on a single piece of a chip or a silicon area. In 1971, they were 2,300. Only these much of transistors could be fabricated with the kind of technology available then. But now it can be 134 billion transistors can be basically integrated on a single piece of silicon, a die. So that is 25 million times more. Similarly, switching speed, it was 1 megahertz for that transistors in 5 decades back. Now it is 5 gigahertz. That is 5,000 times faster. And for doing all this processing, like this, even with this high speed, the amount of power which was consumed by a single transistor was 100 milliwatt, and now it is 0.01 microwatt. That is 10 million times smaller or less. So just imagine your speed is increasing 5,000 times. Your number of transistors are getting increased this 25 million times more, but the amount of power which is consumed by a single transistor is getting decreased 10 million times because the size has decreased so much. And this is integration density, like how many transistors can be fabricated on a area, like a unit area. In this case, it is 1 centimeter square. So 5 decades back, it was only 1,000 transistors per centimeter square. Now it can be 10 billion transistors per centimeter square. Okay, and that is 10 million times. And all these benefits which you have seen above has come at this cost. So cost of fabricating a single transistor on semiconductor material, mostly silicon, is it was $5. So it used to cost $5. A single transistor on a silicon used to cost $5 5 decades back, and now it costs almost. It is I think I calculate it was 1 nanocent. So that is the amount of cost of a single transistor on a silicon, and it is like 500 billion times cheaper to the cost of fabricating a single transistor in state of the art technology now. Okay. And here I'm comparing two leading microprocessors in these two time periods. So Intel 404, this was the name of the leading microprocessor at that time. It only had 2,300 transistors. And now Apple M2 Ultra, this is the leading as a microprocessor used in Apple products nowadays. It has 134 billion transistors. So just imagine how much improvement a single transistor has made, like the kind of properties, the kind of size, the area it is using, or the power dissipation it requires, and ultimately the cost, at which the cost which is being spent to build that single transistor. Everything has improved in last 5 decades. Okay, so this is just something interesting trivia. So the number of transistors which are getting produced or fabricated throughout the year in all the foundries, like all the chips which are getting out of the foundry, and the number of transistors which are getting fabricated on those, it is equal to the grains of sand on earth. So this is the scale which we are talking about. So this is the scale of production. I think there is no other product which is getting manufactured at this scale by the humans, and at this cost, and with this precision. So this is the interesting trivia. Like the transistors which are getting produced yearly, these are equal to the number of grains which are like residing on the surface of Earth. So this is an interesting trivia. And another interesting trivia is just imagine these are some products. I will come back to this first one later. So this is a typical car, and this is a lithographic machine which is used inside a foundry, and this is an aeroplane, and this is a human brain. Okay, And these are the number of parts which are required to build these these products, you can say. So this is a typical automobile car, and it has around maybe 10,000 parts which are required to build it, a typical car, and it costs around 25,000 US dollars. Okay. And this is a lithographic machine which is used, again, a complex piece of machinery. It costs around $100 million, and it has around 100,000 parts to build this machine. Okay. And this is a jumbo jet, an aeroplane. It costs around a single product costs around a $250 million, and it has around typically 8 to 9 million parts in it. Okay. And this is a human brain. Okay. Okay, so we cannot put any cost to human brain, but ultimately human brain is made out of neurons, and there are around 86 billion neurons in a human brain. So all the thinking, all the functionality of a human brain is ultimately done by these neurons, and there are so many number of neurons, then only a typical human brain functions. Okay. And now let us come back to this silicon chip. This is a state-of-the-art chip which we discussed in last slide. It costs $500. The typical cost is around $500. And with the current technology, the latest one, this is NVIDIA GPU. It has 208 billion transistors on it. Okay, so just imagine that these were the regular products which we are using, and the number of parts, like their cost. And this is a silicon chip, which is again made out of transistors, and there are 208 billion transistors on it, and this is the cost of it. But interesting thing is, since brain has 86 billion neurons, ultimately what are neurons? Neurons are also like switches. They are doing a lot of processing inside your brains, like whatever thoughts are coming, whatever thinking you're doing. This is all uh, through those neurons. So a lot of processing is happening inside your. And whatever chips which we are able to fabricate now, they are replicating the kind of transistor which can be fabricated on them. Ultimately, transistors also do something similar kind of functionality. They are also switches. They are basically processing data. The more number of transistors can be put on a chip, the more processing it can do. And then comes the interesting part. Uh, because so many number of transistors are being able to put on a silicon, so typical chips are now basically able to mimic the brain functions, and that's why we are seeing the rise of artificial intelligence. Okay, so I think everybody now knows, like, behind artificial intelligence, there's use of GPUs from NVIDIA GPUs are what they are being used to do all the processing and generate large language models. So just imagine, nowadays the silicon chips which are getting fabricated, they are trying to replicate the functionality of a brain. Again, I'm not telling this is gospel's truth, but this is what we are seeing, because we are seeing now, like, our laptop or machines are now behaving like human brain. Whatever we give inputs to them, they can give answers to us just like a human will. So there is some kind of a silicon processing happening behind it, and that is being done by a integrated circuit of this magnitude. So this Gordon Moore was a co-founder of Intel, and in 1965 he made a prediction. So he was, I think, the first integrated circuit got developed in 1957, and for 8 years he was observing, like, with the improvement in technology and the machines and the processing they were able to do on wafers. He was observing, like, after every 2 years, the number of transistors which are getting fabricated or integrated on a unit area, it is getting doubled. And by that matrix, the cost of getting fabricating that chip was getting halved. Okay, so this was a prediction which he made in 1965. But then this prediction was taken very seriously by semiconductor industry, and they kind of made it into a law. So it is a very famous law. I think everybody from this industry knows it, Moore's law. So what it tells is, like, approximately every 2 years, the number of transistors on which can be fabricated on a unit area, it gets doubled. And also the cost of manufacturing or putting those double number of transistors on a silicon, it gets hard. What it means, like, there is improvement happening in the chips and their processing power, and ultimately the products which they go inside, their costs are reducing. So this is what Moore's law was, and it has been followed till now, although it has lost its relevance a little bit with the leading edge node, but still this is what is being followed till now. And one good example, I think a real life example I would like to share is, I think most of you might remember this was a very popular mobile phone in 2000 time frame, around 2004, Nokia 6600. It was a craze at that time. I remember it had a very good camera, and everybody wanted to have this phone with them. So what Nokia did, like 20 years back, to basically relive the memory of this mobile, the iconic mobile, they launched a similar form factor mobile 2 decades later. It was also called a Nokia 6600, but obviously by this time the technology had increased leaps and bounds. So it was a smartphone. It had a touchscreen. It had a 5G and all the modern features. But interesting thing is, if you want to do an apple to apple comparison, this is a very good example. So this original Nokia 6600, which had just a basic functionality, it could only do the calls. It could, I think, it can click a very good picture, or it can also send a MMS. I think only those were the basic functionality. But this latest phone, it had all the modern features which a typical smartphone had. But just see what the cost is. This phone, the 2004 model, costed $400, and this latest one with all the modern bells and whistles, it costed only $290. Okay, so just imagine, can you find any other industry? Do you know any other industry which can give you a cheaper, much cheaper product, a better product, even after 20 years? No, I think I cannot imagine anything because ultimately everything increases. The price of everything increases with time. But it is only electronics, and that too because of the semiconductors, that we are able to get so much better technology and features, and that too at almost the same price which we used to pay 10 or 20 years back, or even less in some cases. So this is how we are reaping benefits of due to semiconductors. Okay, so I talked about technology node, and I also mentioned like after every 2 years, the technology node it improves or it decreases, and this is the comparison. Like with every technology node, we also saw the new models. That these were the leading edge models at that time, and what kind of features they had, and what was their launch price. So this is just to show you the comparison which I was doing here, rather than from point to point. I'm taking now all the points in between. So in 1999, 180 nanometer was the leading node, and this was the phone, and it only had what it used to offer was only we can only do calling and SMS through that mobile phone, but that also was a very big deal at that time. Then came 130 nanometer node, and this was the model at that time. You could do you like some kind of a color screen start appearing, and then polyphony ringtones. Then in 19 by 90 nanometer in 2004, the first smartphone kind of appeared. This was not Nokia 6600, which I showed you previously. So it had some kind of basic apps. I think, if I remember correct, it used to have a Symbian OS at that time, and also it started having a internet access. So there was a very slow internet on 2G or 2.5G kind of a technology, which was enabled in that phone. And the technology used was 90 nanometer. So why I'm referring to technology is because with the improvement of technology, the kind of chips which were built, all those new features start getting integrated in those chips, and they were finally reflecting into the kind of mobiles which we were getting. But important thing is just see the price. So, okay, there might be some discrepancy here, but more or less the price, if you see the previous earlier slide, next slide also, you will see the price has not increased much. Okay. So this was in 2007. This was the first iPhone, and it was the first touchscreen phone. So this was which basically started the cycles of smartphones. So with the 45 nanometer technology into because at that time the kind of transistors which could be fabricated, they enabled these kind of features. You could have a GPS navigation in your phone, like the Google Map integration was enabled, and touchscreen was a very big deal at that time. Okay, so I think this evolution shows like from 1999 to 2007, this was the improvement in technology node of a transistor, and this was the improvement in the kind of mobile phones which we are getting. And in next slide, this was I think after that the improvement increased many scales, and then started the era of smartphones. Okay, with 32 nanometer, these are the features which started getting enabled. High resolution cameras started appearing, and multitasking. We can run multiple tasks. Like our phones did not used to get bogged down because of opening of multiple apps in our mobile phone. And then 3G, 4G connectivity started appearing in 2012 with 22 nanometer transistor node. And then in 2005, enhanced AI cameras, all the kind of like if you click a picture, you want to improve your picture quality by applying filter, etc. So those kind of features started appearing, and then Siri and all those voice assistant also started appearing. And in 2017, first 5G phones started appearing in the market, and then this one. And now the current one, I think it is only up to 2020, but now whatever latest phone which we are seeing the foldable screen and with all the AI integration, etc. So this is the way, like how the improvement in at least mobile phone technologies happened with all these technology nodes. And similar kind of comparison can be done for laptops and all other gadgets also, because there also we have seen significant improvement over the time. Okay, but important thing is, what I wanted to emphasize is just see their prices. Okay, so this was $200, and this phones were all around $500 to $800. And whatever latest phone which you are getting, they are also around that mark. If you are not going to a very high end, so around 82,000 to 1 lakh, you get a decent quality smart. So just think of like we are getting so much improvement, so much features enabled inside of a mobile phone, but the cost that is not significantly increased, and that is because of whatever improvement this semiconductor industry has made. All the effort which all the foundries and all the design people and all the ATMP people who are working like in the background, they are not in front because they are not generally seen in front. We only see the final product. This is an Apple iPhone, this is a Samsung phone, or this is a Chat GPT, OpenAI, or this is a Google Gemini. But what enables those technologies are semiconductors, and is a big industry. There are people who are working on those technologies to improve them every year or two. Okay, so I think we saw all the benefit of semiconductors. Now, just we will briefly look at what is how a semiconductor is realized basically. So this is a semiconductor crystal. This is derived from silicon. Silicon forms almost 70% of the Earth's crust, so it is very easily available. This kind of a semiconductor silicon crystal is basically generated from a silicon. It is a sand, and then this silicon crystal is melted and converted into these cylindrical form silicon ingots. These ingots are diced, these are cut, and these wafers are derived. Several silicon wafers are derived from these ingots, and then these wafers are sent to a foundry for fabrication to process a wafer. But before doing that, we need to decide like what kind of a circuit needs to be put on the silicon. So there are different kind of circuits: analog, digital, RF, mixed signal. So somebody has to plan what kind of circuits needs to be fabricated. So that is done by a circuit design. This IC design is again a dedicated field of electronics, microelectronics field. So a designer, the team, they build a circuit, they send their design to foundry. Foundry processes those design on these wafers, and once these wafers are processed, they come out of a foundry, and then because on a single wafer, same design is getting imprinted multiple times. So they all these chips they have same functionality. So after coming out of wafer foundry, these chips needs to be basically diced and taken out of this wafer. They are cut using diamond or laser cutters. A die comes out, then this die is basically embedded inside a package. This is what a final package, not a final, but a IC package looks like. Once embedded, a bond wire is connected to make electrical connections to the pin of this package, and then it is sealed from the top. And this is how a final shape of a package looks like. So this is in brief development cycle, how a raw silicon or semiconductor material is converted into a final IC or a chip, which is then used inside products. And a journey of an IC after that looks like this. This is a package IC. And in order to build any product, we have a base substrate on which all those ICs are soldered. And based on the functionality, because for having different kind of functionality, different ICs are required. If you want to have a like a 5G connectivity, you want to have a camera, DSP, or audio amplifier, etc. Based on different requirements, different ICs are required. All those IC along with other components are soldered on a PCB, printed circuit board. These printed circuit boards are embedded inside a smartphone body, along with other components like battery to power your smartphone. There is a camera assembly, and then other connectors, etc. All those are embedded inside a smartphone, and then a final smartphone product comes up. So this is a journey of a integrated circuit to a final product which we finally use. I think whenever we are using a smartphone or any other product, we do not realize all these things are inside it. And this is a journey how that silicon chip or final product come into light from the simple sand or simple silicon to this final beautiful mobile phone. Okay, so semiconductor industry, generally we think of it as a single monolithic, and we mostly talk about only foundries or equipment companies or other, but there are several other building blocks of a complete semiconductor ecosystem. At the top of it, obviously lies foundries because they are doing the most complex job and they are also costly to build, manage, and run. After them, there are chip companies. They basically do all the designing. Whatever design goes onto the silicon wafer, they do. Like if you want to build a 5G chip or 6G chip, you want to build a good microprocessor. These are the companies who do those designs. Then there are wafer fab equipment. I think we very well know about them. All the Lam Research and ASML, TEL, and Applied Materials. So these are the companies which provide equipment to these foundries to do all the fabrication stuff. Then inside foundry, materials are required, all the chemical gases, etc. So these are the companies who provide materials to the foundries. Then there are software companies, because in order to run the fab and also to do the design, specific kind of softwares are required to do the design work and also to do all the process stuff. So there are EDA companies who provide these sophisticated software to enable chip companies to do the design. And then there are IP companies like this ARM, etc., who only do the IP. They do not do any sell products in their name. They only develop the IPs, and then these IPs are bought by chip companies who integrate those IPs into their designs to realize the final IC product. So this is how ecosystem of semiconductor looks like. There are different moving parts to it, and then whatever final products comes out of this ecosystem, they are used by product companies, Google, Apple, Tesla, Facebook, Amazon, all these. And I think these are what we know about. I think their products are what we are using in our daily life, and we relate to them. But beside these companies, there are so many other companies, so many other vendors, etc., who had done their job so that a successful chip comes out of a foundry, and those chip gets then integrated into these products, and then these products goes like a mobile phone or a defense, etc. They go into the final application. So this is a brief overview of how the semiconductor ecosystem looks like. Okay, so semiconductor. Okay, so on the left side, these are the industries which have, by their market value, I think these are the industry which have led the economic growth of the world till now. So these are very big in size: e-commerce, oil production, insurance, real estate, pension funds. These are all the basically non-technical industries which have led growth of world. But just see what are their growth rates. So they, although they are very big, but they are not growing at very fast pace. And on the right side, you can see the industry which have the highest growth rates as of now. So these are virtual reality, augmented reality, AI, machine learning, cybersecurity, e-commerce, green energy, and these have like growth rates in high double digits. But they are, although they have small market share compared to these, but the growth rates are very high. So just see like whatever growth is happening right now in world, these are being enabled by these modern industries, and they are highly dependent on semiconductors. So what I want to emphasize is like the future growth of the planet or humanity as such is being driven by semiconductors. So I think we all know, everybody has heard of Nvidia. They are the like darlings of the world right now. they have grown a lot in last 5 years. And these are the improvement in their financial numbers. They have grown from $3 billion to $61 billion. Market share has increased to 3.5 trillion, and they have a good growth path in front of them. But I think the hidden jewel behind them is TSMC, because whatever GPUs which NVIDIA is building and they are selling to all the AI development, they are being built on the leading edge nodes. These are 4 nanometer, 3 nanometer, and now I think 2 nanometer also. These are the nodes on which all these GPUs are being built. And in all the whatever products NVIDIA is building, I think then TSMC has the 50% contribution to all their manufacturing costs. And as such, also TSMC holds over 60% of global semiconductor foundry market. Okay, so without TSMC, I think NVIDIA is like we cannot basically lower the accomplishments of TSMC. I can say if TSMC is not there, NVIDIA could not have achieved whatever growth or whatever laurels they are getting right now. So just to emphasize what a big role semiconductor fab or a company is playing in development or growth of the world. Okay, so let me, I think I have covered a lot of stuff about like importance of semiconductors. So just to end with few case studies. So on the left side is a picture of it is a this bridge was called a Dragon Bridge. It is like the story is from 1965 to 72 Vietnam War. So there was a bridge which was connecting with North Vietnam to South Vietnam, and it was a very important bridge because it was all the logistics which were getting transported were going through this bridge. And US defense forces, they very badly wanted to destroy this bridge, because if it could have been destroyed, all the logistics could have stopped. So what they did, like, but the issue was like this bridge was very heavily protected. So Vietnam soldiers, they had put all the anti-aircraft machine guns around this bridge. So nobody who used to go near to it, this bridge could survive. So the obviously US, they used their air force and they used to drop bombs on this bridge so that it could be destroyed. But there were no smart bombs at that time. So if you want to accurately hit this bridge, you have to go near to this bridge on the top of it and then drop a bomb. So and that too, you just pray like the bomb hits this bridge. But US tried it for almost 7 years, between 1960 to 72, and lot of they sent lot of missions, lot of their air pilots, airplanes got hit and they were killed, but they could not destroy this bridge. So this went up to 1972. 7 years they could not do it, and as soon as I think in 72 they were able to destroy it, and after that in 3 years this war ended because they were able to choke the supply lines. So the thing is, I wanted to emphasize is like because they were not accurately able to hit their bombs on this bridge, that's why this war got prolonged for so long. And now compare it 20 years later. So this is an example from Operation Desert Storm. It was in Iraq, 1991. So at that time, what US did, they had basically identified all the strategic logistic places of Iraqi army and their government. So as soon as the war started, they started hitting them with precision because they had the coordinates and they had the like fighter jets and bombers who can basically aim their target from standoff and launched the missiles and bombs, and they were accurately able to hit. So Iraq could not sustain this kind of damage, and this war ended within 6 weeks. Okay, so just imagine, US has to spend 20 years in Vietnam War. They could not finish it, but this war they could finish it in within 6 weeks. So what was the difference? So the difference was the ammunition which US had at a time of Iraq Vietnam War. They were not smart, so they were just like you hit send hit like drop the bomb and pray like whether it will hit. But at this time they had all the technologies. They had the GPS, so they knew all the coordinates of strategic locations of Iraq forces, and then they have smart bombs, laser guided bombs. So they had standoff weapons like jet plane can go near to, like it can drop a bomb or it can send a missile from 10 or 50 kilometers away and hit it precisely and then can return back. So Iraq could not sustain this damage, and this war ended within 6 weeks. So and why this? What was all behind all these weapons? All the GPS technology, standoff weapons, laser bombs, smart bombs. It was all electronics, and they are also semiconductors. So within 20 years, semiconductor made such a big difference. Like this war was finished within 6 weeks. So this is how a semiconductor shaped the fate of these two wars. So this was a little old example, 3 decades back. So let us move to the recent one, which we are observing in presently. So this is an example from ongoing Ukraine-US war. So this is a FPV drone, first person view drone. This is a similar drone which we see when we go to any like functions or marriage palaces, and there is a photographer who is filming the party with a drone. This is a small drone, $500 drone. And what Ukraine initially did was it has armed this drone. They basically converted it into in this form. They put a small bomb over it, and they used to take it over the locations of the Russian tanks. This is a T-72 tank, a $3 million tank, and just on the top of it, they used to drop this bomb, and this tank used to get damaged. So this way, they damaged a lot of tanks. So just imagine a small, simple $500, I think it is less than 50,000, $60,000 drone was used to damage a $3 million tank. Okay. And why, what were the technologies behind it? Because they basically manipulated it to enable AI precision into it. They used to put the coordinates of the tanks into it and then send it for a mission. And it used to do its job beautifully. And then the navigation and the electronic warfare. So in order to protect this drone from any kind of jamming, etc., they had built this kind of capabilities in it. So all these features enabled by electronics and semiconductors, which were integrated into this simple drone. And so this that the beauty is like a $500 drone could take down a $3 million tank. So just imagine like how difficult it would be for enemy to sustain this kind of a war. But obviously, after that, a lot of different stuff has happened. But this is how an electronics converted a simple looking drone into a lethal weapon. Okay, so I have talked about all the beauty of semiconductors, all their benefits, and all the great things about it. But one important thing is it is not a cheap uh, art or technology. So here I'm giving you an example of NVIDIA GPU, state of the GPUs, which everybody is talking about. It is in such a high demand to build all the AI stuff. So typical R&D development cost of a NVIDIA GPU is $10 billion, out of which approximately $3 billion is to design that GPU or to do all the architecturing design, circuit design, verification, software, all the activities related to the design. It is around $3 billion. Then the manpower. So there are large teams which are working on these kind of building of chips or ICs or GPUs. So this is the cost which is involved for that kind of manpower. And then during fabrication, cost of fabricating a single chip is around this 12,000 to $16,000 per chip. So in front of this, everything this looks very small. That is ATMP cost. That is testing, packaging, etc. This is $100 per chip. But a final selling price of this chip is around 30,000 to $40,000. So I think if you convert it to INR, it comes around 30 to 40 lakhs. A single chip costs this much, 30 to 40 lakhs. Okay. But this is one thing. This is all about the manufacturing and development of this chip. But since we all know that what kind of role AI is playing in our world today. So the OpenAI's ChatGPT large language model, which I think everybody is like loving it and using it. In order to train that model, 1,000 such GPUs are required. Okay, this is only for training, and for deployment, like the way which we are interacting as a user to enable that technology for user, almost 30,000 GPUs are required. So just imagine like how much cost from the semiconductor point of view is involved, like 30 to $40,000 per chip, and then 30,000 such GPUs. That's why these GPUs are in such demand. But still, NVIDIA or TSMC is not able to fulfill their demand. There is such demand, such cost involved in it, but still they are in less supply. So that's why I told like although we are getting these benefits, the development is very costly, but ultimately the benefits which are these technologies or due to semiconductors are accruing to the users such as us, I think it is many folds more. I think ultimately these companies they do get recover their cost, because as a user we get habituated to this technology. We cannot live without them, and then ultimately they do recover these kind of costs because the benefits are such. Okay, so I think this is my last slide, and I would like to leave with this concept. So we saw these were the kind of mobile phones before 2006, typical feature phones. They used to be there. And over 20 years, these phones have transformed into something like this. So these are the modern phones which are being used now. Okay. So I think what I can see, or we can visualize, I think we can visualize this the same kind of transformation is happening in cars also. So this was a typical like a car in 2004, 20 years back, and this is what latest car. I think if most of you must have heard about it. If not, I think I recommend definitely go to YouTube and view the videos of this car. This is a dancing car. So this is a very funny thing. This car actually dances. So it has motors on its all four wheels. Using it, it can jump in the air and it can do all kind of stuff. So this is what our car looks like now, and this is what will come up in future. Okay, so just imagine what features in modern cars have. So these are the features which smartphones have. These are the features which our modern car is having. All the Bluetooth, Wi-Fi, 5G, the cars have their own operating system. Tesla and all the EVs BYD is releasing, they have own their operating system. Touchscreens, smartphones obviously have, and cars are having big touchscreens now, where through which you can control all the features of your car. All the apps which used to be in mobile phone, they are integrated inside cars now. Voice assistants are there. Electric cars, they are getting over-the-air updates. If you want to change any feature or change any bug in an electric vehicle, that can be done over the air. Then there are autonomous features like facial recognition. It came long back in smartphones. Now the cars are having ADAS kind of features. They are like self-driving cars are coming up. So all the autonomous features are getting electric, and obviously batteries. So all the EVs, whatever battery technologies get developed for the smartphones, I think similar kind of improvement is now happening in cars. So I think the kind of transformation which we see in smartphones over 20 years, same thing we are visualizing in our front of our eyes, right? And I highly recommend please go to YouTube and see what all this car can do. It was amazing to see. Okay, I think that's all from my side. I'm sorry, I think I took a little bit more time.
I think it was a very amazing and full of knowledge session. I will just open the floor for some questions. Let me just change the settings. If anybody has questions which they don't want to ask, but they want to, maybe they don't want to speak up, so that you can, in the question and answer section, you can post the questions, and you will get the answers soon. Rest, I am just unmuting everybody. Just a second.
Shivashna, let me answer your question first. I see why blue light LED was significant.
Yeah, that was Lalit Ji's question.
Okay, so let me answer. So what happened, like in order to generate a white LED, white light, there are three colors needs to be mixed. That is red, green, and blue. Okay. So what happened, like red and green LEDs were invented much before, I think 20 years before when white LED. So that was the missing part. So till white LED could not have been invented or discovered, they were not able to combine these three lights to generate a white light. And in our day-to-day lights, in all the gadgets which we are using, the smartphone or displays, etc., I think white light is what is used in background to light them up. So that was a very big discovery, because then that gave rise to the displays what we are used to right now. Because that was the missing part in that trilogy of red, green, and blue.
Okay, thank you.
Yes, any other questions? Anybody has any other questions? All right, even if you have questions, please, you can, the chat section will be accessible even after the session. I request you to post your questions there so that they all get answered. Uh, Thank you so much, Vipul, for your time, and thank you everybody else for joining the session. And we will keep conducting sessions like these in the future.
Okay.
Thank
Thank
you.
you, Shivasna.
Thank you,
And
Vipul.
Thank you.
It was
Thank
nice
you.
session.
Thank you.
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 Thank you. Thank you.
Thank you. Thank you.
We post also when you give the presentation.
Thank
And
you.
nice session, guys. Come on, keep it up. Keep going, come on.
Thank
Very
you.
nice. Good. Good.